Hey, welcome to another video. So in this video, we're going to talk about some features of polynomials as far as what they do graphically. These are super important and they're also super cool. What they do is they allow you to picture what the polynomial is going to do, sketch it, and get a fairly accurate picture with minimal work. What we're going to talk about is multiplicity, so what in the world that means, and what end behavior does, and turning points a little bit, and that's at the very, very end. So we're going to talk about multiplicity first, what exactly that means in relation to the roots or zeros or real zeros or x-intercepts that you're going to get from a polynomial after you have factored it, after you've found some sort of x-intercept in that function. So we'll talk about exactly what that does, how it relates to a graph of that polynomial, and then what the end behavior does as far as when you graph it. We're not going to be graphing today, but we're getting a fairly clear picture of what's going to happen when we get there. So let's talk about multiplicity first. What in the world that means. What multiplicity refers to is a repeated zero or root or x-intercept in a polynomial or any function really that you're talking about. So what that means is if you can factor a polynomial, which I've given you one that's factored, and you have the exponent, that exponent is going to determine the multiplicity of that particular zero, or how many times that zero is repeated. And I'll talk about that in just a little bit, what it's going to do for you, because again, I don't like suspense. So at least not when I'm teaching. So here's what multiplicity is going to do. Multiplicity is going to say, hey, take all of these factors that you have, set them equal to 0, because we know that we can find x-intercepts for any function when we set it equal to 0, and look at the exponent. That exponent will determine multiplicity and will tell you one of two things. Whether that 0 that you get from every one of these factors that has a variable, don't worry about the 7, doesn't really matter as far as your x-intercepts. Take every factor that has a 0 or has a variable, set it equal to 0. What that 0 is going to do, it's going to either bounce or touch the x-axis, or it's going to cross it, depending on what your multiplicity is, whether it's even, 2, 4, or odd, 1, 5. You can say right now that this 0 is going to create a bounce or a touch on the x-axis. So is this one. That's a cross, that's a cross. Why? I'm about to explain that to you, but that's what's going to happen. So let's go ahead, let's walk through the process, let's find multiplicity, let's talk about the zeros, talk about what a repeated root is, why it's called multiplicity, multiple roots, talk about what those exponents do, and then get a sort of a picture of it down here. So if we ever want to find x-intercepts of a function, including polynomials like what this one is based on, this is just a factored version of a polynomial. If we wanted to do that, if we want to find x-intercepts, we set that function equal to 0. So when we do that, if you were just, let's excuse the notation here, just put that equal to 0 and say that function is now equal to 0, then in order to find x-intercepts from a factored version of a polynomial, we set every factor that has a variable in it equal to 0. And that's called the zero product property. If we know that several things are multiplied together and that equals 0, then each of those factors can set equal to 0 will maintain that statement. So saying, yeah, if x equals 0, it makes this true. If x equals 2, it makes this true. If x equals -1/2, it makes this true. If x equals -3, it makes this true. That's the zero product property, kind of in a nutshell. And we're doing the exact same thing. Fortunately, we have all this factored. What if it wasn't factored? I'm going to teach you that in the next section. I'm going to teach you how to get to this point from a, let's see, degree 12 polynomial, because there's no general way to factor that without knowing zeros, so we'd have to have that in the first place. So let's go ahead and let's use the zero product property. There's a couple things I would like you to do when you're going through this process. Number one, for every factor that has a variable, make sure it's in parentheses. This looks great, this looks great, this looks great, but in order to not get confused on our multiplicity, what I'm going to do, I'm going to build parentheses right around that x, because that x itself is a factor that we're going to set equal to 0. I don't want you to get confused with the 7. I don't want you to get confused with that power 2. As far as being a root itself, x is going to be a 0. The 7 has absolutely nothing to do with that. I know that's a little bit confusing. So what's a 7 do? The 7 determines the kind of a factor that lets you make it more dramatic. Like remember when if we just had x to the second power, we'd say, all right, we know what that is. That's a parabola. If I put a 7 in front of it, what's that do to the parabola? It makes it very narrow. It does not shift it. It doesn't shift the vertex of that parabola. That's still at the origin, but what it does is it narrows it. What if I put a -7? Well, that narrows it and reflects it. It doesn't change the vertex at all. It doesn't change the x-intercept at all. And so this coefficient of leading term, really, this coefficient of leading term has nothing to do with the x-intercepts themselves. It has to do more with the shape of the graph and whether or not we are reflecting it. It will affect how we interact with the x-intercepts, whether we cross it one way or another, but that comes a little bit later when we start graphing. So, long story made short, factor your polynomial, we got it. Make sure that you have parentheses around every factor that has a variable in it, like this one, this one, this one, and now that one. That's great. And now we're going to set all those factors that have variables equal to 0 by the zero product property. So, all right, well, what do we have then? We have x equals 0 and x minus 2 and x plus 1/2 and x plus 3 equal to 0. Well, that's the zero product property. Now we solve them all. All right, that's pretty easy to solve. This one's already solved. So just x equals 0. I'm going to write it again just because I want all of them to be here for us. And if we add 2, we get x equals 2. And x equals -1/2 if we subtract 1/2. And x equals -3 if we subtract 3. So let's see, 0, got it, add 2, got it, subtract 1/2, subtract 3. These are all of the x-intercepts that we can possibly have on that polynomial. There's only 4 x-intercepts. Now wait a minute, I told you a little while ago that's a degree 12, and I'm going to get to that once we finish this example, like how I've determined the degree 12. It's that sort of fake distribution that I showed you. I'm going to show you how to find the leading term in just a little bit. But these are all the x-intercepts. So why aren't there 12 of them? Well, because we run into a repeated 0. You go, what's a repeated 0? A repeated 0 or a repeated root, repeated x-intercept, is when your factor has a power that's more than 1. So for instance, what you could do with this, it would be super awkward, but what you could do with this, instead of writing this 7x squared and then x minus 2 and then x plus 1/2 to the 4th power, you could do something a little crazy. You could write this as 7 times x. That's the same thing as 7x squared times x minus 2. And this is where it gets a little crazy, times x plus 1/2 times x plus 1/2 times x plus 1/2. And you could do that again, x plus 1/2. I'm going to pause there for just a second because hopefully you're going to get the point right now. We could do that. This is still 7x squared times x minus 2 times x plus 1/2 to the 1, 2, 3, 4th power. Here's the point of multiplicity or repeated roots. Could you set x equal to 0 and x equals 0? Yes. Are you going to get 2 different roots? No. Are you going to get the same root twice? Yes. And that twice, you get in the same root twice. That's what multiplicity means. It's a repeated 0. You're getting the same thing twice. And that determines what happens with your graph. That's really cool. It's so valuable when we get into polynomials and we get into graphing rationals, is knowing how many times that root is repeated will dictate whether we bounce or touch the x-axis or whether we cross the x-axis just based on the number of times that 0 is repeated. I'm going to tell you why when we get down to here. So you could set this equal to 0. Let's see, x plus 1/2 equals 0, x plus 1/2 equals 0, x plus 1/2 equals 0, x plus 1/2 equals 0. But you're going to get x equals -1/2 4 times. That 0 is repeated 4 times. That has multiplicity 4. That's going to tell you that we're bouncing off the x-axis at x equals -1/2. That's awesome. That's very important for us to know. This you could do 5 times. I'm not going to write it because it's really annoying. But you could write x plus 3 times x plus 3 5 times. You would get x equals -3 5 times. Do you actually need to do that in order to understand you'd be getting the same root 5 times? No, you just need to know what exponents mean. Exponent means a repeated factor. So we have a repeated factor, repeated twice. We have a non-repeated factor. It's only repeated, well, it's actually not repeated at all. They just have that same factor once. We have a repeated factor 4 times, a repeated factor 5 times. That is what multiplicity means. So frankly, you do the zero product property without worrying about the exponents. You get your zeros or x-intercepts, or, well, real zeros or x-intercepts, or your roots, and you look at the exponent from where you got your zero. You look at the exponent that is on the factor from where you got your zero, and that is your multiplicity. That's how many times your root is repeated. So what we would say here is that x equals 0 has a multiplicity of 2. And x equals -2 has a multiplicity. Give it an exponent. Make sure all of your factors have an exponent. They all will. This has a multiplicity 1. X plus 1/2 has a power 4. What that means is that this 0, this x equals -1/2, has been repeated 4 times. That's a multiplicity 4. And lastly, x plus 3 has a power of 5. That means that this 0 would be repeated, or this x-intercept is repeated 5 times. You get 5 of them. If you wrote all that out and set them equal to 0, you get the same 0 5 times. That's all multiplicity means. How we use it is very powerful, but that's all that it means. This is multiplicity 5. So if I can recap real quick, which I'm going to because I'm making a video. Here's what multiplicity means and now what it does. Multiplicity means take a polynomial and factor it. From those factors, if you set the function equal to 0 to find x-intercepts, from those factors you will get zeros or x-intercepts or roots. If we do that, use the zero product property and then solve them, these are the only 4 real zeros or real roots or real x-intercepts that we get. The number of times they're repeated comes from the exponent above each factor from where you got your zeros. That's how many times the 0 would be repeated, and that right there is called multiplicity. Now here's what it does. Depending on whether your multiplicity of your 0 is even or odd, it will tell you whether you bounce, or sometimes we call that touch, the x-axis, or whether you actually cross it. So it's not about the value of the x-intercept itself. It's about how many times that x-intercept is repeated. Multiplicity means multiple times of repetition. So we look at this and go, all right, this 0 is repeated twice. It has a multiplicity 2. That is an even multiplicity. I don't super care that it's 2. I care that it's even or odd. I care whether the multiplicity is even or odd. This 2, this x equals 2, this is not repeated. You only see it one time. That factor only appears once. That is a multiplicity 1. We'd say that's odd multiplicity. Right there, that shows you, I'm not talking about the evenness or oddness here. That's not the thing. The thing is how many times we've been repeated, that's multiplicity, and whether that number is even or odd. And I'll explain why it does this after I finish. X equals -1/2, that's a repeated root 4 times. That's multiplicity 4. We really need to understand that that is an even number of repetitions of that 0. Even multiplicity. And lastly, multiplicity 5 says that factor's been repeated 5 times. That 0 would come up 5 times if we went ahead and worked all that out and set each factor equal to 0. That multiplicity 5, that's great. What I care about is that multiplicity is odd. And here's the whole interpretation for us and why it works. If you have a 0 with an even multiplicity, man, all zeros, all roots, all x-intercepts, if they're real numbers, which you can't get there without complex numbers if you're just factoring normally. So if we're getting real zeros, real x-intercepts, all of them are going to intersect the x-axis. That's why I call them x-intercepts in the first place. They all intersect the x-axis. Every one of these, every one of those numbers, you're going to have your graph in some way interacting with the x-axis at x equals 0, and x equals 2, and x equals -1/2, and x equals -3. This graph will be there on the x-axis. However, how it intersects, depends on what your multiplicity is. If your multiplicity for that 0 is even, then this graph is going to, we call it either touch or bounce off the x-axis. It's going to go down and go boop, or come up and go boop, and bounce right off of it. It will not cross. In other words, it looks something like this. Either your graph is going to come down, touch, or come up and touch, but it will not cross. Now I'm going to answer the question why. Why does it do that? Why does that even make it bounce and not cross? I want you to think on sort of a microscopic level for just a second, and we call doing that like a neighborhood. So you live in a neighborhood, probably, where you have some neighbors around you, some points around you, but it's not talking globally, all right? So when you say neighborhood, you're sort of zoomed in to like where you live. So we're zoomed in to where these x-intercepts right here live. And around that neighborhood, what you would have is you say, hey, if we have an even multiplicity, what happens when you have an even multiplicity? That's like a power 2 or a power 4 or a power 6. What happens when you take numbers to the second power or the fourth power or the sixth power? Well, they're all positive. What that means is that on both sides of that x-intercept that has an even multiplicity, so around x equals 0, let's imagine like this is 0 for a second, around x equals 0, then you would square the numbers. What's going to happen? Well, they'd both be positive, yes, but I want you to think more importantly, they'd both be the same sign. So they'd either both be positive, or if I reflected it, both be negative. They'd have to have the same sign around the neighborhood of that x-intercept. So for evenness, for even multiplicity, around these zeros, x equals 0 and around x equals negative 1/2, if I take something a little bit to the left of that, just a little bit over here, little neighborhood, or a little bit over here, little neighborhood, and I plug that in. And then I say, okay, take that value, subtract 1/2, and then square it. Around that neighborhood, you're going to get the same value of an output. Either both, at least a sign, both positive or both negative. It's not quite symmetry, so I hope you're hearing this. It's not exact symmetry around that, but it will at least have the same sign. Either both positive, or if I put a negative in front of this, both negative. And it sort of depends when we get a little bit further on whether you're bouncing coming up and going down, or bouncing, coming down and coming up. I'm going to explain that to you in another video, but the main point here is that in a neighborhood around that x-intercept, if you have an even multiplicity, a root that's been repeated 2 times, 4 times, 6 times, etc., then what's happening is that your neighborhood around the x-intercept has to have the same sign, both above or both below the x-axis. I hope that makes sense to you. I hope you're kind of getting that, hey, even multiplicity is going to bounce or touch, going to look like this around that x-intercept. And the reason why is because the neighborhood around that, you have to have the same sign. As far as odd goes, if you have a 0 or a root with odd multiplicity, you're going to cross the x-axis at that point. So you'd look something like this, or that, either coming down and crossing or coming up and crossing the x-axis. Why? Well, because we know that with odds, once we get a different sign, so if I pick a number, let's say this, and do this again. Let's pick, how about just 2? Here's x equals 2. Now look at where that 2 came from. That 2 came from x minus 2. Imagine picking a number in a neighborhood that means very, very close. That doesn't mean 3. That doesn't mean 5. That means like 2.000001. A neighborhood is really tight knit. Compared to the world, your neighborhood is super small, okay? So if I pick something in a neighborhood of 2, like 2.01 or 2.0001, 2.000001, so something right close to 2, but just bigger than it, what's going to happen? Well, something just bigger than 2 minus 2 is going to be a positive number. If I take a positive number to an odd power like 1 or 5 or 7, 3, 1, 3, 5, 7, any of those odds, it's going to maintain that sign of being positive. I'm going to say that one more time. You really need to get this. So if I take a number that's slightly bigger than 2, and I subtract 2 from it, I'm going to get a positive value, and I take it to an odd exponent, it's going to maintain that positivity for me. I'd get a positive. That's above the x-axis. Now, take something in the neighborhood just smaller than 2, like 1.99. Okay, take 1.99 and subtract 2. Well, wait a minute, that's negative. Yes, it is. Now, a negative to an odd power, what's that do? Well, that maintains negativity. Negatives to even powers don't. Negatives to even powers maintain the same sign as if you were positive. It doesn't really matter because we know that even powers maintain sign for both positives and negatives. Odd powers switch sign. And that's why we cross for odds and that's why we bounce for evens. Because in that neighborhood, if I have an even, whether I'm above or below the number, I get a positive or negative, yes, but when I square it or take it to the 4th power or 6th power, it gives me the same sign. When I have an odd, if I'm above or below in that neighborhood, it's going to give me a positive or negative, yes, but odds maintain the sign of that. So for positives, things bigger than that, I get a positive, and for negatives, taking it to an odd power, I get a negative. That's above and below, or below and above the x-axis. It's going to cross it. Here, that's above than above, or below than below, because it maintains the same sign. I hope that makes sense. Maybe watch that again to get the point of, in the neighborhood around your 0, you'll be positive or negative, but the way that your exponent interacts will either keep the sign the same, or reflect it, keep the sign the same, or change the sign if you're odd. Evens keep it the same. That's why they're sort of quasi-symmetrical around that. That's why they maintain the same sign. They're just going to bounce. But odds don't. Odds switch sign, that's therefore we cross. So I hope that makes sense. That's what multiplicity does for you, and we're gonna use that. The last thing I wanted to tell you before we get into end behavior, maybe after we get into end behavior, I'm going to show you how to fake distribute that to recap that. So we'll get there in just a minute. All right, so now it's time to move on to end behavior. These two things, if you haven't realized it yet, these two things are going to be super important for our graphing. We just learned a minute ago that multiplicity, what it does is basically tells us if you can find your x-intercepts, which we're going to be able to do after the next section. We're going to be able to factor it as much as possible over linears or irreducible quadratics. We're going to be able to do that. We're going to be able to use the zero product property. We're going to be able to count exponents and say, hey, this is a double root, or a single root, or a quadruple root, or a quintuple root, or basically multiplicity 2, 1, 4, and 5, and determine from that whether we have even or oddness. We talked already about how evenness maintains sign in the neighborhood around your x-intercept, and therefore you'll bounce, maintain sign, either for positive and negatives, you get the same sign out, bounce, or for odds, you cross. Different signs, different outputs. That are opposite signed outputs. And that's going to tell us whether we're going to bounce or cross around the x-intercept. That's very valuable for graphing. We need to know that. The second thing we're going to learn today is about end behavior. What end behavior does, it says, because these polynomials are all continuous, we'll talk about that in last, they're all continuous, there's no gaps, there's no jumps, there's no holes, asymptotes, there's no cusps. They're these really smooth, flowing curves that go to and from infinity somehow, all along the x-axis, unless you start restricting domain, which we're not. We already learned that domain of polynomial functions is all real numbers. Plug it in anything. There's no room for a domain issue. Well, what that means is that our end behavior is going to be one of 4 cases. Our 4 cases are, you can start from negative infinity on the y, I'm talking outputs here, negative infinity and go to positive. You can start at negative and go back to negative. Start from positive and go to negative, or start from positive and end with positive. Think about the cubic function, x cubed, looks like this, and the quadratic function, x squared, looks like this. That's positive to positive or negative to positive. You're going to get one of these 4 shapes on any, I look like I'm dancing now. You're going to get positive to positive, negative to negative, negative to positive, or positive to negative as far as our infinities are concerned. That's the only 4 things we ever get out of polynomials. And it all comes from the leading term of your polynomial. I told you in the last video it was important. This is where the rubber meets the road for the leading term. So if we look at our polynomials, the leading term, all that means, if you need a little refresher, is that if you put this in order, it's the first term that you see. It should be the term with the highest exponent. That's your leading term. So in our case, our leading term is 3x to the fifth. Here, our leading term is not negative 2x to the third because that's out of order. So if we took just a moment to write this in order, our leading term would be negative 5x to the fourth. Here's the point. Within a finite interval of the x-axis, your function can do a lot of really cool things. But outside of that, it's going to behave as far as your leading term dictates. Your end behavior is determined by your leading term. So if we think about like way out there on the x-axis, it's going to be determined by this. So this is going to look end behavior-wise a lot like, I'm going to use squigglies to say approximately. So like the end behavior is going to look approximately like 3x to the fifth. At least that's what it's going to look like when we get out to the infinities. X approaches negative infinity and x approaches positive infinity. We're going to see what that looks like. And for g of x, it will look approximately, not modeled exactly, but approximately like negative 5x to the fourth. So all we need to understand is what those power functions look like. Do you remember that last video? So the power functions are basically looking at your leading term and saying, hey, what's that going to be? Well, that's an odd. Well, what do odd functions look like? Well, around the origin, they're symmetrical about the origin. And around the y-intercept, or y-axis, evens are symmetrical about the y-axis. So here's what this would look like. This says this is a positive, hey, 3 is positive, odd type of a function. Odds look like this when they're positive. So why am I leaving the middle not filled in? Because this is end behavior only, what's going to happen is that this function is going to start by coming up, increasing. It might do some sort of turning points, things like that, and then it's going to end increasing. That's the point. When you put this in conjunction with what you're doing around your x-intercepts, it's extremely powerful. With these two things, multiplicity and end behavior, if you add just 2 more to them, any y-intercepts that you have, and any turning points you can identify, you have a very, very powerful graph. Turning points are really identified in like a Calc 1 class where you take derivatives set equal to 0 and you go, oh, that's probably a turning point. Let's just do a sign analysis test. And it's not that hard. Here, we're not there yet because you don't know what a derivative is yet, but you will. And keep this in mind when you get there, that if you know multiplicity, oh my gosh, students usually forget it. And then I have to refresh it or they never ever really put it together. Use that in end behavior and you have a very powerful graph. So for our leading term, you go, yeah, that's a leading term. That gives me end behavior. I know it's odd. Odds look like this. Or if I have a negative, they look like this. For evens, you go, well, evens, this is our leading term, negative 5x to the fourth. I know even functions look like this. Or if they have a negative, they look like this. Why? Well, because even power functions have to be symmetric about the y-axis. Why is that? Because if I take positives and negatives and I take them to the 4th power or 2nd power or 6th power, it's going to be the same sign out. If I reflect it, it's still the same sign but negative. That's the same exact logic that we use with multiplicity. It's why I paired these things together because they have very similar concepts. Odds don't work like that. Odds say if I take positives and negatives and take them to an odd power, I get out a positive and a negative respectively. Or if I reflect it, a negative and a positive respectively. It's going to reflect, but they're going to be opposite signs. So odd, opposite. Odd, opposite. That means cross. Even, the same. Even, the same. That means bounce. Same exact idea that we're using, but now it's on a grand scheme. It's saying, hey, look at your leading term, let that be a power function for you, and then determine that is a negative even. Even means the same, but negative means downward opening. So this would look about like that. Now some interesting things might happen in the middle of this. We might get some x-intercepts, that'd be determined by this. We might get some some turning points that are not associated with the x-axis, and we'd have to identify those typically with calculus or estimate them. But that's about it. So one more thing, what if we change some signs? What would it do? If we change this to, let's say, negative 3x to the fifth, then what that would say is you're an odd, you have opposite signs, but now I'm reflecting it. So now it would sort of do that. I'm trying to color coordinate for you so that the opposite there would reflect your graph. Totally reflect it, actually. Here, if we change this to a plus, then instead of downward, we'd sort of get a upward opening, at least as far as the end behavior is concerned. That would be an even, sure, but positive means you'd come from positive infinity and end at positive infinity, or at least heading that way. That's what end behavior does for you. The last thing that I want to talk about is this. I mentioned turning points a couple times. What a turning point is in a graph is where you have a local, that means in a little neighborhood, a local maximum or a local minimum. So where you take your graph and you are increasing, then change to decreasing, local max, or decreasing, then change to increasing, local min. They're basically like a little peak or a little valley somewhere in your graph. If your polynomial has degree whatever, in this case degree 5, there it is, or in this case degree 4, there it is, that's always from your leading term, then you will have one, well at most, one less turning point than your degree. What that means is that if your degree is 5, you can change directions at most 4 times. So if you're a degree 5 and you know that you go from here to here, let's say you're a positive degree 5, well, how many times can you change direction to still make that work? Well, you can do 1 change 1, 2, 3, 4, but you can't do a 5 because you'd end at the wrong infinity. So to make this work, you can have at most 4 changes to make you still end up with the end behavior that you need for a degree 5 polynomial. Even if you reflect it, still at most 4 changes you can do without messing up your end behavior. Or likewise, imagine a power 4, degree 4. A degree 4 polynomial should either end this way or this way. It's even, it has to. It's based on that sort of symmetry idea. At least from our power function. That's why we have approximately. It's not exactly symmetrical, but it's based on that. So if you have to end this way, so degree 4, you can have at most 3 turning points. That would be down, then up, that's 1, up, then down, that's 2, down, then up, that's 3. What if you did a 4th? Well, you'd be facing the wrong way. You'd be an odd. So you have to have at most 1 less than the degree number of turning points. Does it have to be that many? No, it doesn't. It really depends on what's happening in your function, but it doesn't have to be that many turning points. It's just at most that many. The last one, I've said it already, but every polynomial, because of its domain being all real numbers, there's no room for any sort of asymptotes. It's like a kind of a force field that you can't hit. It makes a sort of weird gap in your function, or a hole, or a cusp. A cusp is just a sharp point. It'd be like going like this, and then a sharp point. There's no room for that in polynomials. They're not that interesting. So every polynomial creates a continuous, this is continuous, curve with no cusps, no sharp points. That means they are continuous everywhere, and also later on in calculus, they're differentiable everywhere. It means you can find a derivative or a slope of a curve at a point, slope of a tangent line to a curve at a point, everywhere. Basically, they're the least interesting graph that we have because there's nothing weird about them. And that's pretty much it. That's what I need you to know about polynomials at this point. Next time we'll focus on starting to find functions from zeros, and then after that we're going to graph them. So it's pretty cool, but hopefully you can see how important this is to graphing. Man, if you can factor and you know your zeros, your x-intercepts, from your factor, zero product property, and you can find repeatedness, multiplicity of your roots, you know whether you're going to bounce, bounce, or cross. That's very important. I explained to you why. If you know your end behavior, so basically just your leading term, you know whether you're going to end this way, this way, this way, or this way, just by reading whether you're odd, that means opposite, associate odd with opposite, positive or negative, or even, positive or negative. That's it. The last thing that I wanted to talk to you about, I mentioned it. I said after we finished end behavior in this multiplicity, I would show you again how to fake distribute, because the multiplicity here is very easy, but your end behavior might be eluding you. You go, I don't remember how to do that. With your end behavior, what we can do is sort of fake distribute this. Distributing this would take a very, very, very long time. You'd have x plus 3 5 times, you'd have to FOIL it 5 times, FOIL, because you have a lot of inside outsides and distribute. So instead of doing that, use the same concept that we had, that there are 1, 2, 3, 4, 5 factors here, one of which is a sort of a constant factor. And then what we're going to do is multiply them together as far as the largest powers that you would get from distribution. So we take our 7 times x to whatever power is here, your multiplicity, x squared, times x to whatever power is here, x to the first, times x to whatever power is here, x to the fourth, x to whatever power is here, x to the fifth. That, I guarantee you, will be your leading term if you took the time to distribute all this. Don't forget the 7. It's pretty important, because you know that if that 7 was negative, it would reverse your end behavior. So keep that 7. And then we know that if we're multiplying x's, we're going to add those exponents. That's 5, 9, 10, 11, 12. That's 7x to the 12. So right now, what's the end behavior? You should picture in your head what the end behavior is. Is the end behavior odd? Well, no. Is it even negative? No, because the 7's positive. This end behavior will look like this, guaranteed. That is so powerful. When you have it in conjunction with your multiplicity, all of which has to work together, you get a very clear graph with almost no work. Now, finding the factors, yeah, that's a lot of work. We deal with that in a couple videos, but at least we have that. So again, if I changed the sign, made that negative, that would now be an even. So same sign, but reflected, so downward opening. Man, I hope that's made sense to you. Oh yeah, one more thing. If this had been an irreducible quadratic, if that had been an irreducible quadratic like x to the second power plus 3, don't forget that you would have to multiply these. So you'd have 2 times 5, that would give you 10 here, not 7. You would multiply that. And the reason being, you'd have x squared plus 3 times x squared plus 3 times x squared plus 3 5 times. So if you were to distribute that, you get x to the 10th. And then here you'd see, oh my, you see 17. Yeah, 7x to the 17th. That would be an odd if it's positive this way, or if I put that negative back, that would be an odd reflected. Okay, now I hope that makes sense. So you talked about multiplicity, you talked about end behavior, we've done an example of that fake distribution to get the leading term, where we get end behavior from, and next time we'll start wrapping all this together. So I hope you enjoyed it, and I'll see you for another video.